Weir. He's going to talk about the primordial gravitational wave from first order phase transition. Yes, please go ahead.
Thank you for the invitation. Just work out how to do things. Okay. So can you hear me okay in the room? Is the sound on Zoom okay? Hopefully somebody will complain if they can't hear me on Zoom. Okay. So first I'd like to thank the organizers for the very generous invitation. It's lovely to be here for the first time in Korea, and I have had some really nice discussions. I've met people that I otherwise haven't had the opportunity to meet, and I've really enjoyed all of this so far. I mean, we're going to have to talk for 45 minutes, so I think 45 minutes. So I'm going to talk to you today about some of the work I do on studying phase transitions in the early universe and thinking about those. Sorry, is it off? I'll turn stuff off. Okay. Yeah, should I keep talking? Yes, no problem. I'm going to basically maybe tell you about the complementary application of gravitational wave cosmology to what Professor Kim was saying this morning. So Professor Kim was talking about how you can use kind of things we already have seen with gravitational waves. So we've seen black hole mergers, and we've seen neutron star mergers, neutron star black hole interactions, and we can use some of the evidence from those to place constraints on the Hubble, the Hubble rate. What I'm doing in some sense is a bit more speculative and is about a much earlier, more primordial phase in the history of the universe. So if I think about, if we look at one of these, famous pictures of like the history of the universe, when you think about the CMB, that's formed about 380,000 years after the Big Bang. But if you want to probe what happened before that, you can't look at the sky and look at photons because the surface of the last scattering at 380,000 years after the Big Bang is as far back as you can go. Before that, the universe is not transparent. So then you might ask yourself, well, maybe I can look at I'll find other ways of probing what happened at that stage in the history of the universe. And one of them would be gravitational waves, because gravitational waves, once they're produced, don't interact with anything. They just propagate freely towards us at the present day. So that's one nice thing. And I'm interested from my own area of research, in particular in what I'm going to tell you about today, what happened a few picoseconds after the Big Bang. So the universe was kind of thumb-sized, 2 centimeter horizon size. And at that time was about the time we think the electroweak phase transition was happening. That's the time I'm interested in. And I'm going to tell you why it's possible that there might be gravitational waves produced at that time in the history of the universe, what they would look like, and why it matters. And there's many reasons why you might want to have a first-order phase transition at that time. Baryogenesis is another one if you want to think about electroweak baryogenesis. But I'm going to focus purely on this as a phenomenon that you can observe and use as a constraint on particle physics theories. But furthermore, you could even imagine that there's some rich physics in a dark sector that we don't have access to, except maybe through a very small portal coupling. And then you can use gravitational waves produced during some sort of non-equilibrium physics in that sector as a probe of the physics as well. So gravitational waves provide a valuable probe, and as I'm going to argue hopefully today, they probe the physics beyond the standard model at around electroweak scale, particularly when one thinks about the future missions like LISA. So the LISA mission is coming in the next 10 to 15 years. It's currently in reaching the end of what's called phase A, when they kind of define the contracts which will be written to build the spacecraft. This is an artist's impression of one of the spacecraft here. You often see these artist's impressions with big red lasers shining out of them, and I don't think they're very realistic, so I prefer this one where the telescopes and the lasers don't have any weird red laser light shining out of them. But what will LISA look like? LISA will have a typical arm length of about 2 to 3 million kilometers. So in some sense, it'll be a triangle of 3 satellites. it'll be the largest human-made structure in some sense, because there's 3 satellites in a triangle orbiting the sun, each satellite separated by about 3 million kilometers, shining lasers at each other. And these 3 satellites, they do a cartwheel orbit around the sun, follow behind the Earth, about 20-ish degrees behind the Earth, but in a heliocentric orbit. And it's a joint mission between the European Space Agency and NASA. The European Space Agency is the lead in this part, but NASA is providing some key instrumentation as well. And so, yeah, we're on to we finished phase A, sorry, we're on to phase B1 now. These phases of space missions always confuse me, but we're on to phase A now. And so this is just to give you an idea of the perspective on how big these things are, and these little telescopes which will receive the laser light. This is about 10 times the nominal Earth-Moon distance, this nominal distance between satellites. So these satellites are very well separated, and you're shining a laser at a satellite which is millions of kilometers away, and you have to use a telescope to enhance it, and then send it back again, because you want to time the distance between satellites. So this is technically very difficult to do, and it's quite impressive that it will work at all, but it will work. Lisa is going to see a lot of things. One thing Lisa will see is, Professor Kim mentioned these black holes merging to each other, and he also mentioned the fact that you can see long before the final moments of the merger, where they do the final in-spiral, you can see them orbiting each other and producing gravitational waves kind of almost monochromatically for a long time. And that's actually one thing that Lisa will also see. So you can, in this kind of plot of all the kind of menagerie of signals that Lisa will see, these lines here are LIGO-type black hole binaries. So these are the years and years before they'll merge in the LIGO band. These lower frequency gravitational waves from these LIGO black hole binaries can be seen in Lisa, and then they slowly increase in frequency as the black holes get closer and closer together, and then eventually they leave the Lisa band at about 10th of a hertz, and later on down here they'll enter the LIGO band, and you'll be seeing them in Earth-based detectors. One reason why, so Lisa has a sensitivity around a millihertz. You can't go down to those frequencies on Earth because of seismic noise, and basically the size of the Earth means that you can't physically get a thing more than 4 to 8 kilometers in size. But you can see the early stages of these things here. These kind of yellow and red bands here are a similar story, but for supermassive black hole binaries. So these are black hole binaries with tens of millions of solar masses in very distant galaxies merging at high redshift. And then the thing which I want to draw your attention to most of all here are little blue dots and the blue stars. So the blue stars are so-called verification binaries. And these are compact binaries, say white dwarf binaries typically, mostly in the Milky Way, that we can both see with telescopes, optical telescopes, and we expect we'll be able to get the gravitational wave from. And these, because they're 2 binary stars orbiting each other, if you've done any gravitational wave physics yourself, you'll know that they almost are monochromatic in the gravitational waves that they produce. And so it's very easy to kind of tune. You'll need these to tune Lisa to detect gravitational waves, and that's why it's called a verification binary, because you'll be able to verify that it works with these. So these are, I mean, there's about 10 of them marked here, and there'll be probably order of magnitude 10 to 100 for Lisa that will be used to tune Lisa. And I think of these as like 57 or so stars that navigators used to use to sail across the seas. There are these 57 stars that they would see, and they would have to find them in order to work out where they were. Lisa needs to see these verification boundaries to know that it works properly. But these other blue dots, these form a foreground of tens of millions of galactic white dwarf binaries. And there's many of them which are so at low enough signal-to-noise ratio that they actually form a background here. So this is kind of some of the things which, to me, as a cosmologist, form a foreground. And I'm actually interested in a stochastic background from primordial physics. And in order to see that, we will have to understand and remove these foregrounds to see some sort of background which might be lying underneath that. So that's another challenge. And I'm not going to talk about the challenge today. I'm not going to talk about that challenge of removing these foregrounds, but I want you to know that it is a challenge, and working on it is a kind of open problem as well, to dig down beneath all these other sources which are astrophysical in nature, to understand what, if any, stochastic background from early universe physics there might be there. All right. So just as a nice, this is a nice application of like the time-temperature relationship that you can use. If you assume that the gravitational waves get redshifted on the way to us in the kind of usual way as they climb out of like the well of history, and if they're produced at very large scale, so very close to the horizon size at the time in history of the universe when they happened, if you think about the QCD phase transition, which happened about 10 to the minus 3 seconds, that's about 100 MeV, with about 10 degrees of freedom participating, then if you plug the numbers into the relevant equations for cosmological history, then you get gravitational waves that are typically about 10 to the minus 8 hertz. So earlier in the week, we heard a little bit about pulsar timing arrays. And so this is why, for example, these QCD scale phase transitions might be provable by these pulsar timing arrays. We heard this morning about the end of inflation, and end of inflation, depending on when it happened, depending on the energy scale of inflation, happened much, much earlier with the same or more degrees of freedom than are in the standard model. And that means that you have gravitational waves at very, very high frequencies, which you would not be able to directly detect, but which leave a fingerprint on the CMB in terms of B modes, so you can indirectly detect those. But what I'm interested in, what I'm going to tell you about the rest of today, are what would happen at around the electroweak scale, which is about 10 to the minus 10 or 11 seconds, at about 100 GeV, with 160 degrees of freedom that you typically see in the standard model. And that produces gravitational waves. If you plug these numbers in, then if you assume that it produced at about the horizon size at that time in the history of the universe, that produces gravitational waves that are a fraction of a millihertz, basically. So that's the time in the history of the universe I'm interested in, and I'm going to focus on today. So the question then is, could physics beyond the standard model produce stochastic background of gravitational waves? And my argument, and what I want to sell to you today, is that these are a valuable way of probing new physics that would be in a dark sector and therefore out of sight of particle physics experiments entirely, or potentially at higher energy scales, or hidden from colliders for some other reason. So that like one of these like nightmare scenarios or something like that. So these give you a way to probe particle physics, and that is not, otherwise not accessible. So I'm going to kind of, as a framework to think about these things and to present some of the things I've been working on over the past few years, I'm going to think of this as like a pipeline. And at one end of this pipeline is the question of what particle physics models are reasonable and could work, and how do they work and why. And at the other end is what would we see if these were true? So if we have a model, what do you see? And I want to take you through, again, my personal approach to doing this. So the various stages in the history of, or in the calculation of going from a particle physics model through to a cosmological gravitational wave background. So starting with a Lagrangian for that model, and then using high temperature effective field theory to make it easier to study with lattice Monte Carlo simulations, and then using some, there's a kind of relatively small number of parameters that actually parameterize the way in which these gravitational wave, these phase transitions proceed. So then you do some simulations of those to produce an expected gravitational wave power spectrum, and then you make general inferences from that. So this is sometimes, if you read the kind of white papers about this is often called a pipeline. So you start like, you kind of put a model in at one end and you do some stuff, and then at the other end you get out energy density and gravitational waves. So this is, I'm going to talk about my own personal, entirely selfish and partial approach to calculating some things along this pipeline. So let me start by thinking a little bit about the first half here and what goes on up there. So let's just assume for the time being that the model is some extension of the standard model with some BSM fields that couple the standard model fields. So it's just a simple extension of the standard model in some sense, just to be concrete and think about something in particular here. So what does the standard model electroweak phase transition look like? So what I mean by this is the time and the process at which the Higgs boson turned on and developed a VEV. Now, in fact, in the standard model, so if everything that we've seen so far, so up to including the Higgs, and forgetting about the leptons for now, is all that there is, then there's actually no phase transition at all. The Higgs field would just flop down from the symmetric phase to the broken phase without any non-equilibrium physics whatsoever, in a process known as a crossover transition. It's not even called a transition, it's just a crossover. Because there's no latent heat involved, there's no discontinuity of any order parameter, the VEV just very smoothly turns on. So if you think about the Ehrenfest classification of phase transitions, there's no discontinuity in the order parameter, so there is no phase transition there. But it's very possible, and indeed theoretically quite elegant, that in extensions of the standard model, it would be first order. So you'd have some effective potential, which at high temperatures above the critical temperature would only have the symmetric, the true vacuum, and then that would become the false vacuum as the temperature falls to some nucleation temperature, at which time the fields tunnel through to the new true vacuum, and you nucleate bubbles of stuff by tunneling from here through to here, or thermal fluctuations taking you over the top there. And then these bubbles of the true vacuum that form in the false vacuum, as they expand, when they collide, bubbles themselves are spherically symmetric, and spherically symmetric bits of stress energy do not source gravitational waves because they have vanishing quadrupole moment. But when they start colliding, they develop a non-zero quadrupole moment because things are no longer spherically symmetric. And that's when you get gravitational waves starting. So when things start colliding, you're going to get some gravitational waves produced there. All right. So what does the standard model phase diagram look like? So this was something which was very heavily investigated in the 1990s. So people wanted to understand how heavy would the Higgs have to be in order to have a first order phase transition. Back then, for reasons like, as I mentioned, understanding electroweak baryogenesis and other things. So this was verified by various groups in various ways. And it looks a bit like this. So if you put the Higgs mass on the x-axis and you put the temperature of the universe on the y-axis, then about 75 GeV is the end point of a critical line for this phase diagram. So if the Higgs had a mass of less than about 75 GeV, it would, this is just a minimal standard model, then it would experience a phase transition, a first order phase transition. But as it happens, of course, we have a heavier Higgs than that, and it goes around the end here, and it does not have a phase transition at all. And if you're the sort of person who collects universality classes for field theories, it was also discovered or confirmed that this critical point at the end here is actually Ising universality class critical point. So you can, but we're not going through the end there. So we know it's definitely a crossover. So it's not an Ising phase transition either, but it would be if we happen to hit the end there exactly. All right. How did people do this? Well, one way in which this was calculated was using this notion of high temperature effective field theory. What does that do? Well, it's something which is especially used for people looking at, for example, QCD. You do this a lot, but it's also been applied successfully to the electroweak sector. And the basic idea is that if your temperature of your system is very, very high, then at long distances larger than the inverse temperature, it looks three-dimensional. So this is just the kind of basic realization that you can use. And then you can write down a Lagrangian for your three-dimensional theory and calculate Green's functions at finite temperature in your 4D theory and at zero temperature in your 3D theory. And basically look at the two of them and think very hard, and then work out which ones correspond to which other ones. And then it lets you write down a list of couplings in the 3D theory and how they relate to the couplings in the 4D theory. And that means if you tell me that my 4D theory of the particle physics model as these couplings or whatever, I can then match that on to couplings exactly in 3D theory. And that's quite nice because if you do the thermal field theory in 4D, and you're interested in the physics that happened at the phase transition close to where the fields are becoming light, so masses get very, very small as you go to the phase transition, so the fields become very, very light. Then the expansion parameter has the mass on the denominator, so the expansion parameter, if you were going to do this perturbatively, gets very, very big, and this is known as the infrared problem of thermal field theory. So if you do this in 3D instead, then you don't have that problem because you're no longer expanding, and the expansion parameter doesn't have the mass on the bottom anymore. And in fact, there's other nice reasons to do this as well, but then the light fields can be studied numerically using lattice simulations, for example. Yeah, sure.
So the question is, one usefulness of this dimensional reduction is because the barrier, which is required for the first order phase transition, can be triggered only by the bosonic mode, and only for the bosonic mode you do have a 0 busbar frequency. So that's why, and under this dimensional reduction, only bosonic mode survives, for example, yes. Right? So all the fermionic mode decouples. So in order to understand, therefore, whether there is a useful or strong enough barrier, therefore you actually can see whether it's going to be first order versus second order and so on. I do see that it's extremely powerful, and it can save a lot of time and effort. However, my question is, if you were to really understand the full dynamics of phase transitions, which seems, I think you wanted to simulate in principle to extract a lot of the phase transition parameters, and then you feed it into the next level of a simulation, then is this three-dimensional reduction captures all of the physics that you actually need to fully understand, maybe not fully, but understand enough to extract informations that are required for the next process.
So thank you for the question. So your concern is about the fact that the fermions are just discarded or integrated out, or is it?
Not only that, right? You're not only integrating out the entire fermionic mode tower, but you're also integrating out heavy bosonic tower as well. So my question, therefore, is theoretically whether the nature of a phase transition is really controlled by the mass, like the light is the mode. Once you do this dimensional reduction,
that's a good question. And so I think, yeah, we can talk about this more offline, but I'll also show in a couple of slides a plot which kind of shows you, like, basically what the heavy bosonic modes, where it takes you in parameter space. So if you're thinking about trying to get a phase transition, actually the inclusion of the heavy bosonic modes is not important. It's always light modes that matter.
Okay.
So if you're yeah, I'll show you, and if that doesn't answer your question and you still want to talk to me now, then we can discuss it then.
Cool.
And if not, then we'll talk offline later.
Yes.
But thank you for the question. It's an important point, and it's a key thing that we need to deal with. So thank you for that.
Thanks.
Yeah. So in a couple of slides, I will have a thing to which might elucidate that. But in the meantime, you can map this phase diagram onto, if you have just a minimal standard model of a SU2 doublet and an SU2 gauge field, not even worrying about Weinberg angle, so you can forget about the U1 because it doesn't actually change the physics very much from this point of view. Then you can map it onto two parameters. One is basically a quartic coupling in 3D, which we often call X, which is dimensionless, and the quadratic mass parameter, which we often call Y. And then it looks a bit like this. And you have an endpoint of this phase diagram at about 0.11 for X. And so 75, if you do this matching and you plug in the mass for the Higgs, and you work in a reasonably sensible renormalization scheme, you think about things carefully, then you'll end up with X is about 0.11 there. And the physical Higgs mass, more or less, is about 0.29 in X. So it's, again, beyond this endpoint. But one of the points is that with dimensional reduction, the mass scale of the new fields can be heavy enough that it can be integrated out and discarded, and then you can go back and check this as well. So that's one of the things that happens. If you do that, if you assume that the new physics is heavy enough that it can be integrated out, then the minimal standard model takes you to somewhere here. So all the theories which have additional degrees of freedom, BSM degrees of freedom that are heavy enough, they basically are to mass, their masses are of a scale much larger than the Higgs field, will end up in this rhombus here. And this parameter dimension just give an idea of what's going on here. So the x-axis here is the strength of the phase transition. So that's basically how much energy in the universe is participating in the phase transition. And then the y-axis here is the inverse phase transition duration. So that tells you how long, well, it's 1 over basically the time relative to the Hubble rate of how long the transition is lasting. So if this is larger, then the transition happens faster. And so you get more bubbles produced very quickly. We're going to come back to these parameters later, but I wanted to show these plots now anyway. But the thing to point out, I wanted to point out with this plot is that if you do a 4D perturbative calculation for some benchmark points, it'll land you here. The equivalent perturbation calculation in 3D, the 2 loops, will get you here. And if you do this, if you then do lattice simulations for the same parameter point, you end up here. So this gives you an idea that like how the systematic uncertainties for typical one of these typical cases with this standard model effective field theory, which is not really standard model effective field theory, and how close it gets to. And for you to have an observable source of gravitational waves from this, or even in principle observable, you would need to be down in this corner here. And so you're nowhere near here at all. You're well away from this. So heavy physics, heavy additional degrees of freedom they can in principle produce first order phase transition, but the parameter space where they lie is such that you're very far from being observable here. So the question then would be, how do you escape this corner of parameter space? So if you make if you tune your theory to have cancellations at some loops, then that takes you parallel to the region where things are observable. If you have large couplings or add lots of fields, it again takes you parallel. The only way in which you escape this corner of parameter space to go towards having an observable signal from a BSM theory is to either have higher dimensional operators or add some degrees of freedom which are dynamical at the energy scale at which your dimensional reduction is done. Does that add extra? Yeah. Okay. So that's my point. So basically, if it's heavy physics, I'm not interested in it because it will basically land you somewhere in here, which is very far from observability. So additional degrees of freedom that you need to see in order to see something from those, they need to be light, or they need to involve higher dimensional operators. All right. So however, so this means it has to be of a temperature. It has to be at this scale here. So it has to be integrated out at pi t, so 700 GeV or GT. So these two scales. So if it's much heavier than g squared times t, then it would be removed during this process, and it wouldn't appear at this light scale. And if it is light, then it needs to be included in the 3D Lagrangian, and then you need to do all this process with that included. So one example of that is here. So this is an example where we did a simulation with the minimal the Higgs doublet, and we had a triplet field, so a standard model adjoint field, which is labeled sigma here. And this, what we do here, we did a full lattice Monte Carlo simulation of the phase transition in this triplet extended standard model. And on the x-axis here, you have the temperature. And on the y-axis, you have the plot of the condensates, I think in NS bar. So that's why they go negative. And what you think about is if you lower the temperature here, now remember I mentioned these are order parameters, and if you have a phase transition, then the order parameter would have a discontinuity either in the first or second derivative. To be a first order phase transition, you want to have a discontinuity in the first derivative. And the points, if you look at the points to start with, then these are lattice results from doing a fully non-perturbative simulation here. If you go here, you go down, the first you get for this benchmark point, this is just one choice of parameters. You lower temperature and you first get a small discontinuity in the triplet field. So you have one phase transition here. And then that jumps back to the symmetric phase, and instead the Higgs jumps to the broken phase. So now you get a relatively strong first order phase transition for the for the Higgs field, sorry, here. And that's what's happening here. And then it goes on developing a Higgs VEV there. And the triplet goes back. And this is what's known by people like Michael Ramsey-Musov call a two-step transition here. But the reason why this is interesting is that if you then try to do your best effort with perturbation theory, so you have a two-loop perturbative calculation here, the perturbation theory firstly gets it, this is more than, well, about 10% away. So the temperature at which transition happens according to perturbation theory is 10% away from where the transition happens in the lattice simulations. And secondly, like firstly, the perturbative result doesn't ever have a discontinuity. But if you were to call this the jump, then it massively overestimates how strong this transition is here. So there are these systematic errors, which is why one of the things I want to argue to you is that you shouldn't trust perturbation theory all the time. All right. So the key points so far. So if you do dimensional reduction and you use lattice simulations, then you have a reliable, as long as you work within kind of the realm of kind of your own ignorance, you have a good method for studying theories beyond standard model. But in order for it to produce a strong phase transition, if the fields are coupled to the standard model fields, then the physics has to be light. It can't be heavy fields because they will end up somewhere far from the region where you have a strong phase transition observable with. Yeah. And the other thing, the other reason I would say that is that when you do the 3D theory, you write down a certain number of operators, and even with just the standard model, like usual standard model in 4D, that can induce high dimensional operators at 3D, which don't map to 0 in the 4D theory. So if you're going to that certain region of parameter space, then your 3D theory has to have you have to write down additional operators, which you then have to include in this process of matching. So it's not yes, you can have an ab initio, higher dimensional operator in the 4D theory that you have added for some reason, but it could also be that there's higher dimensional operators induced in 3D, which you have to match onto. And if you just ignore those, that's a limitation in the accuracy of your 3D theory there. Yeah. So the question, just for people on Zoom, was: am I including, or is one including the higher dimensional operators only that are induced, or ones which are already there in the 4D theory? Is that the question? Or yeah. So in the calculations I've shown you in this half of the talk, we've not included any extra operators. We've always been just looking at a very minimal model with extra. We've not been putting in extra operators. All the operators we have have been. We've not added high dimensional operators. No. Yes. Yeah. So we've not. That's not something it's something people have actually not done. People have not looked at this kind of adding higher dimensional operators and seeing what the consequence is from these things. It's something which should be done, but it's not been done yet. But thank you for the question. All right. I'll move on now to talk a bit about the other half. So this is, again, I'm giving a bit of a guided tour of my own favorite bits of this, and I'll give you an idea of how to calculate these things. So if you've done this simulation and you've got the kind of plots of the field condensates I just showed you, that lets you calculate the phase transition parameters for these theories. So let me now firstly talk about what these two parameters I wrote down here, what they are. You saw them briefly on one of these plots, but I'm going to tell you what they are again. And then show how these have consequences for how you simulate the early universe physics that you might produce a gravitational wave power spectrum from. So there are several key parameters, and these parameters don't depend on the actual underlying physics. These are generic parameters which kind of are they're very model generic, should we say? And these include the phase transition strength alpha, which you can think of, as I said, is how much energy is released during the transition or how much participates. One level is the latent heat, but it can also maybe be thought of more accurately if the idea of a trace anomaly is familiar to you. So like, which is maybe a generalization of latent heat. It's best to think of it as a trace anomaly rather than just as latent heat, but it's the amount of energy that's released during the transition. Then there is this beta, which is the inverse phase transition duration, which you can think of as kind of the tangent to or the rate of change of the nucleation rate during the transition. Because nucleation rate, as you go down below the nucleation temperature, it explodes. And so how quickly the nucleation rate explodes is parameterized by beta. The temperature which that happens is Tn, the temperature which bubbles nucleate, which is less than the critical temperature. Could be a lot less if it's supercooled. And then there's the speed at which the bubbles expand in the plasma. They're in a plasma, they're expanding, and they're heating up the plasma, and the plasma's applying friction to them, so that slows the bubble walls down. So they reach an asymptotic speed VW. And there's a couple of other parameters, like, for example, the number of relativistic degrees of freedom matters as well. But the basic four are these four here. All right, so what happens during one of these transitions? Well, the first thing is bubbles nucleate when you get to the nucleation temperature. And like I said, the nucleation happens explosively or very, very rapidly at that point. And this happens on a timescale driven by this inverse phase transition parameter beta, so 1 over beta. The bubble walls expand, and you can imagine this, if you imagine this is like these are slices through one of our simulations, and this is the kinetic energy. So these rings are the bubble walls heating the plasma and forming reaction fronts around the bubble walls. That's what you see in these things here. The bubbles and these reaction fronts collide, and that's when, as I mentioned, you get gravitational waves produced. And then after the bubbles have collided, you're left with just pressure waves moving through a plasma, and pressure waves moving through a plasma are sound waves. And it's these sound waves which are one of the main sources of gravitational waves from these scenarios. Then, if you have waves of stuff moving through a viscous medium, they will eventually become shock waves as the energy gets dissipated and pulled to shorter length scales. And then you will get some form of turbulence happening as you get eddies forming. So things get, energy gets redistributed to shorter and shorter length scales. And eventually these things, turbulence taking energy down to the dissipation scale of the shear viscosity of the system, or damping, because this is happening in an expanding universe. So you could just get Hubble damping. These things will turn this off, and then things stop. Okay, and these three stages at the end, the bubbles colliding, the reaction fronts of hot plasma colliding, the sound waves that are left behind, pressure waves moving through the system and overlapping with each other, the shocks, the turbulence, these all produce gravitational waves in different ways. And these are all important. And my talk today is not going to be a detailed discussion of how to calculate these, but maybe a quick run through of some interesting open issues with these that I think are interesting and that we've been recently working on. But just to go back, I want to talk a little bit more about these things. So this kind of assumes that the wall velocity is relativistic, so it's maybe a tenth the speed of light or so, but not exactly the speed of light, or doesn't accelerate to large boost factors. There are exceptions to this. One are the so-called vacuum transitions, where the field which is undergoing transition is not actually coupled efficiently, or doesn't basically, typically if it's not doesn't have any local symmetry, then it doesn't couple very strongly to any gauge bosons, for example, or for example, if it just doesn't have any strong coupling to the standard model, then it will feel like it's in a vacuum, and it'll expand very rapidly and accelerate to very large boost factors. Or potentially it could be that it does have local symmetry, but the gauge bosons, the effect of the heavy gauge bosons is so small that it accelerates and the friction isn't big enough to stop it accelerating to very large gamma factors as well. But if they do, then as I said, the plasma, well, I didn't say it, but the plasma motion will last about a Hubble time because it's expanding, and the Hubble time gives you the time scale in which things damp. And the fluid motion, as I said, there's these shocks and turbulence, and the fluid motion becomes nonlinear on a time scale which you can actually just work out from dimensional analysis. So it's the typical size in the system, which is the typical radius in the bubbles when they collide, and then the typical fluid flow velocity, or I don't know why it's used U, but it's a fluid velocity. So you get this, if you divide the length scale by velocity, then you get a time scale. And this just is dimensional analysis, and that tells you the time scale in which things become nonlinear in the system. All right, so this is now a movie. This is just a quick movie showing what this process looks like, at least initially, after the phase transition. So these are rings around the bubble. You don't see the bubble here. You're just seeing the kinetic energy in the plasma. This is a movie of the plasma, not the ring, not the Higgs field. And it's a slice through a 3D box. Okay, so you see stuff coming into the plane, and this is because bubbles are being nucleated out of the plane and coming towards you. So then you see things happening later on, like these here are bubbles nucleated out of the plane. This is also being streamed over the internet, so the video is a bit slow. Sorry for the jerks. If you watch this on your own laptop, it'll hopefully be faster. But yes, and then they collide, and you get after these bubbles have collided, you have these pressure waves just passing through here. So this is the kind of thing we're simulating. This is showing, again, I want to emphasize, this is the 3D. Sorry, this is the kinetic energy in the system, not nothing else. And you get these bubbles have collided, and then you get these rings of pressure passing through, and it's these intersecting rings of pressure which source the gravitational waves mostly. All right. Like I said, if you watch this movie on your own laptop, it might be less jerky.
So when you say this simulation includes only the kinetic energy of the system, you just mean, for instance, you're missing the fact, for example, there will be surrounding plasma in the false vacua, and then as the bubble expand, of course, there can be some like turbulence, whatever the interactions between them. You're saying those effects are not included. That's why you said it's kinetic journey.
Thanks for the question. Sorry, no, I misspoke. So I mean that I'm only showing the kinetic energy here. The simulation which underlies this is a 3D relativistic hydrodynamic simulation where the source of the heating of the plasma is actually a scalar field which is expanding and which is heating the plasma through friction. So this is an effective model of what's going on in this system. This is coupled field and fluid system. I don't want to go into the details of these simulations because it gets quite technical, but we can talk about that offline if you want. But yeah, the simulation includes a field which models the scalar field undergoing transition, a friction term which models the interaction between the bubble wall and the plasma, and a relativistic fluid which models the plasma.
Okay, I see.
Does that answer your question?
Yes,
yeah.
Thank you.
Okay, thank you for the question. So if you do this, then you get results like this. So this is on the x-axis here, we have the wave number scaled by the radius of the bubbles. And the y-axis is a bit difficult to see, but this is the gravitational wave power spectrum energy density per logarithmic frequency interval. And you get this kind of peaked shape here. This red line here is an ansatz, which is often used to describe this scenario. And the high frequency power law here is wave number to the -3, this blue line here. And what we've done here is, because this sound wave source, like the source of these sound waves sourcing gravitational waves, is basically on until Hubble damping removes it. We've scaled this out by t. So the fact that these lines for different times fall on top of each other at the end is that you're sourcing gravitational waves continuously. So sound waves in the plasma are a very efficient source of gravitational waves until Hubble damping or turbulence happens, and these change what's happening a little bit here. All right. So then, if you want to calculate, if you have that, you have some simulation, you have some results for what the gravitational wave power spectrum looks like. Then, if you want to calculate whether you'll see this scenario or not, you have to plot your gravitational wave source, and you have the sensitivity curve for your gravitational wave detector. And the thing you actually want to measure is not, you don't just want to plot these things together, but actually what you need to do is you need to measure the signal to noise ratio. So I want to emphasize, because I think it's often the case, people plot these two things and they think, oh, well, I'm done. The thing you actually need to worry about is whether the ratio of these two actually produces an observable signal to noise ratio. So you have to integrate over frequency, calculate ratio of the two, integrate over frequency, and multiply by the observation time t here to get the signal to noise ratio. But I think this here would be very observable. Like this would probably, if I remember correctly, this case I took here had a signal to noise ratio of several hundred or so. So this is very clear. But what we've not included, and as I mentioned in at the start of my talk, this to have good theoretical understanding of this, and in order to detect something like this at LISA or somewhere like that, or to rule it out, we need to handle astrophysical foregrounds properly. And so one of the big open problems in our subfield is now correctly and accurately making predictions and modeling the foregrounds, that when we see something or when we don't see something, we can set constraints on, or we can announce the discovery of gravitational waves from one of these sources. All right, so in the final couple of minutes, if it's okay, I'm going to very briefly talk about some of the open questions that I mentioned in this field, which are what happens to nonlinearities during transition. So everything I've talked about so far has been sound waves, and sound waves are longitudinal waves. Like I'm talking to you, I'm producing sound waves, and the sound waves I'm sending to you are not turbulent, right? They're just compression waves passing through the air. But actually, this system has sources of viscosity, and those produce these seed vorticity as well. So there's various sources of vorticity here, and they will make it turbulent. So that will be different from just the sound waves that I've talked about. And then after the transition, so there'll be shocks and turbulence, and what we also call acoustic turbulence, which is interesting as well. So I'm going to talk about two of these things very briefly, just to give examples. I'm going to talk quickly about droplets, which are these heated regions, and they're not so different from what you talked about. This is why I asked you this question earlier in the week. So we have these heated droplets which remain over the symmetric phase afterwards, and they're held up by the pressure due to additional heating there, which I'll show in a moment. And I'll also talk briefly about what I call acoustic turbulence. All right, so if we have here we have a simulation of a strong phase transition. So the speed of wall velocity is less than the speed of sound, which is why this is called deflagration, but that's not important. And the strength of the phase transition is relatively strong. This is about 1/3 of all the energy in the universe is in this. And here, this version, these movies here, made by my former student and postdoc Daniel Cutting, the white here is the bubble wall, and then the more bright these colors are, the larger the fluid free velocity is. And what we see here is that firstly, you get vorticity generated behind the walls. You can kind of imagine that you've got these kind of vortical flows here. The other thing to bear in mind is that you have these little long-lived droplets here. So these take a very long time to evaporate. This bit here of the symmetric phase, now it's finally gone. So if you have, and then you can see that this is quite, there's a lot, if you can do the curl operator with your head, then you can see that this has got quite a lot of vorticity here. If you do curl of V on this with your eyes, you can see that this is a very vortical flow, and this is before turbulence has even started. So strong transitions tend to lead to very vortical flows, which I've not talked about today, which are not well understood yet. But they also lead to these droplets, these things lying around for a long time, like I mentioned. And these, if you think about this in terms of the speed of the walls in the system, the stronger the transition, so the larger alpha is, and if you then measure as a function of time, the speed of the bubble walls, they accelerate, and they reach kind of an asymptotic speed. And for small transitions, they can stay at the asymptotic speed, and then the bubbles all disappear. But for strong transitions, like we saw, the walls slow down, and then these droplets live for quite a long time before they finally evaporate. That's what we saw in the previous plot. This case here is what we saw in the movie we just saw. So the wall speed accelerates to almost to the asymptotic speed you'd expect. Then it slows down. Of course, most of the system is gone, but the little bits that are left, you're left with these droplets which are very slowly evaporating. And these are very bad for gravitational waves if these were to exist. So if we think about the wall velocity here, and we think about if we instead don't look at this y-axis, instead look at these contours here, these are how strong the transition is. If you go to this region here, we have very small, slow wall velocity and very large a very strong transition, then if you can calculate the suppression of the gravitational waves, and this could be like 1,000 what you'd naively expect for the gravitational waves here. So it's really these droplets are really bad they really slow down the production of gravitational waves if they exist. So that's one of the quick things I want to talk about. The other quick thing I want to talk about is acoustic turbulence. This is where actually you have overlapping shocks in longitudinal degrees of freedom. And this is something actually which has been looked at for a long time in the literature in fluids, but it's not the same as Kolmogorov turbulence. Kolmogorov turbulence is this idea of vertical eddies going to smaller and smaller scales, and it's very it's well understood, and I think it's in Landau and Lifshitz, and everyone in principle everyone can look at it. I have not looked in detail at it, but it's a fairly familiar phenomenon. But the idea of overlapping sound waves producing what we call acoustic turbulence is a relatively less well-studied thing, at least from the point of view of particle physics and cosmology. But what we can see here is, if you initialize, this is a 2D movie by, or a 2D simulation of just a non-relativistic fluid by, this is buffering, damn it. Well, you can look at the movie yourself if it doesn't quite load, but we'll give it a minute to load and I'll just keep talking. This is a movie of a 2D non-relativistic fluid by my student Yanni Dao. And here in this movie, we initialize the system with just some like basically purely longitudinal flows in the fluid. And we add a lot of viscosity. And what you see is that it steepens into shocks. So you get this field of overlapping shocks. Let me just go back and forward, maybe it'll load faster that way. Or maybe not. There we go. So you see, anyway, at least you can see the start of this. So it steepens into these shocks there, like that. Let's run start again. So you start off with things, and you see like this, these flows, and these are shocks that are overlapping there. And this produces a very different spectrum of gravitational waves than you get from other sources, so from the sound waves and things. This is a very different way of doing things. So this is what, so I want to emphasize the difference between acoustic turbulence and normal Kolmogorov turbulence. So acoustic turbulence is where you have a cascade from long length scales to short length scales in longitudinal degrees of freedom. And Kolmogorov turbulence is about eddies in vorticity. So you have big eddies and they become smaller and smaller eddies. And so these two things are both ways of transporting energy from long length scales to short length scales. And they both are important when you have a lot of power at long length scales. So, Kolmogorov turbulence has been widely looked at everywhere, but acoustic turbulence, I think the first paper looking at this in a cosmological context was this paper by Penn and Turok 4 or 5 years ago, where they looked at this, and that kind of gave us inspiration for this study as well. These shocks naturally form if you have some viscosity. So the viscosity causes the fluid to steepen. And then as it steepens, when you get these shocks, they start to interact with each other and they pull energy to shorter and shorter scales. So that's why it's called acoustic turbulence, because it does this cascade to shorter length scales, which is, from a physicist's point of view, the underlying thing which happens in turbulence is that you take energy from long length scales and you take it to shorter length scales. So that's why it's called acoustic turbulence, because it affects longitudinal degrees of freedom, but it does the same thing like turbulence would do, except, Does that answer your question? Okay. So anyway, the movie is yours to watch if you look at this on your laptops. But the key thing, one thing I want to say here is that one thing which is different about, this is a result from our paper. Again, we have the wave number here scaled by some length scale, and this is just the spectral shape for this. And the k to -3 might be the same as we saw for sound waves, but this k to the 5.5 power spectrum with intermediate length scales, and this k to the 9 here as well, are completely different, and these are unique to acoustic turbulence. So you might be able to infer from the actual spectral shape, if you're able to reconstruct it, what kind of physics was going on during this transition, basically. All right. So let me thank some of the people that have been involved in this. So some of my students, so Yanni Dahl, I mentioned, did the lovely 2D simulations. And then Anne Kormo, my PhD student, Sato and Essi, who did some stuff on the droplets and things. Postdocs, so Diana Hooper, who's currently with us, Laura Niemi, who used to be, and then my other more senior collaborators, well, Daniel Cutting and Oliver Gold and Jonathan Kozaczuk as postdocs, Mark Heinemarsh, Stefan Huber, Michael Amzamusov, Kari Umakainen, been people, and I've worked with more senior collaborators, and also here we have Hiren Patel and Thomas Tenkin, who've also been postdocs who've moved on elsewhere. And this is some of us walking through the forest during the pandemic. We couldn't meet in the office, so we went to the forest to go for little hikes instead. So that was that. All right. So if I want you to remember two things. Early inverse processes can probe by understandable physics, but in order for us to do that, we need to precisely calculate the parameters that we have. Perturbation theory is not necessarily enough. And so my recommended solution is that we simulate representative theories with lattice Monte Carlo simulations. And the other thing that I tried to make clear in the second stage is that we're still trying to understand how nonlinear physics like acoustic turbulence, droplets, and other physics, which happens towards the end of a phase transition, matters when studying these phase transitions. And has consequences for other phenomena as well, like what you were talking about. And these, in order to understand these, we need to do more large-scale cosmological simulations to understand how these things work. And if you want to ask me difficult questions, I've given you 3 questions here. You can ask me about. I think I'm done. So thank you for the time and thank you for listening.
Thank you very much for that talk.
Hey, Evie.
Thanks for the super clear and very interesting talk. So one of the question I have was, I think you mentioned that once droplet is formed, especially when VW is very large, and that tends to have a suppressed gravity wave signal, if I heard you correctly.
Yes, yeah.
Okay. Do you have some intuitive explanation why that happens?
Sort of.
Okay.
So you're referring to this case here.
Right.
Yeah. So one thing I should say is that this is a very finely tuned case, right?
Very fine-tuned, you
Very
say.
fine-tuned. So you have to go to very small wall velocities,
Right.
which means basically you have, and typical BSM models actually end you up over here. So this is kind
okay.
So you have to be quite finely tuned to be at this particular point here. But why it happens? No, I'm not sure.
Okay, but numerically it turns out to be the case, you mean?
Yes, so numerically it definitely is the case, but the underlying processes are still under investigation. So like we need to understand, more work is required, as they say.
I see.
Especially when, that's why I tell the people who give me funding anyways, that we need to do more.
And one related speculative question is, how long the lifetime of this droplet can be? In other words, can we even imagine that even today or whatever, like sometime around this time, whether there can be actually electric symmetric droplets around us? And is it reasonable, or that really requires super tuned parameter space for that to happen?
That's a good question, and we've not yet seen them, which I think disappoints my colleague Kari Rumokainen, who would love for us to see them, but we have not seen them. One thing I would actually point out is that here, the fact that these, so we would expect these, like this very weak transition here, it asymptotes to constant velocity, and that's what you'd expect. You expect walls to expand at a given speed, then they collide and they go away.
Right.
But then here you notice that this slows down and it also reaches a constant velocity. And what we think is happening here is that, so hydrodynamics, relativistic hydrodynamics has no length scale in it.
Okay.
So there's nothing, there you have you have the viscosity length scale, which is very short length scale.
Okay.
And that's the only length scale you have. So hydrodynamics is very susceptible to making similarity solutions, which are parameter independent. So what we actually think is happening here is you're getting a similarity solution of a droplet shrinking. Okay. So the droplets become self-similar.
I see.
And that's actually what we think is happening here, is that you're getting you've reached a point where the droplets are self-similar and getting smaller.
Oh, really? Interesting.
But then they have to, that then means that they have to have a velocity parameter, right? They wouldn't, if they wouldn't be stable. They wouldn't be self-similar if they didn't shrink.
I
So
see.
they would have some time scale associated with them. If they
Okay,
were
I see.
constant.
Interesting.
So the fact that these become potentially these self-similar solutions, which we have evidence for here, and also in this paper we put out last year, we have some evidence for that,
Cool.
makes me think that this particular mechanism of getting stable objects doesn't work. I mean, I think it's possible you would have them, but in this case, they shrink and eventually evaporate.
Interesting. Okay, thank you so much.
But thank you for the question. It's a good question.
Any other urgent question?
Hi, can you hear me?
Yeah, thank you for the nice talk. I just have a very naive question on, so the parameters that you discussed about the bubble dynamics, can you give a brief explanation of whether the thickness of the bubble will also affect the gravitational wave spectrum or the underlying physics of it?
So thank you. That's definitely not a naive question. Thank you for asking. So yes, so firstly, the bubble wall itself, of course, is at like inverse the mass scale happening, right? And then that's very, very, very small. And these things are happening on Hubble horizon scales, right? So this is very, very, very big, and there's 10 to the many orders of magnitude difference between the two. So the bubble wall itself is unlikely to have effect on these bigger things. But my understanding would be that one thing which does matter, which is very closely related to that, is the coupling from how the effective coupling between the scalar field and the other degrees of freedom. And that in some sense is reflected in how the bubble wall dynamically looks, because it back reacts on the bubble wall. So if you just naively solve for some bound solution or whatever, that gives you a certain shape. But the actual shape, when you consider the back reaction from the fields that are interacting, will be very different. So my answer would be not immediately, but the general consequence is that yes, it will. The microscopic physics associated with the bubble wall is super important. So it's not a naive question. It's an important and open question in the field. Thank you.
Thank you very much.
Okay, last question.
So another
Hello,
thing,
can you hear me?
I imagine when you have the phase transition happening, you are liberating some energy density that may inflate the universe. So is it true or?
Yeah, so you can. I mean, if you have enough energy density when you nucleate the bubbles, yes, it can inflate. One reason why, for example, we try to keep alpha order of magnitude less than about 1 is that my own naive assumption would be that if it's bigger than 1, then that's reaching a point where the energy involved is such that inflation could happen, and then you have to worry about like doing calculations of bubble expansion in curved space-time, which I don't want to do. I leave it to other people to do. So yes, it does matter, but in these cases, and it should be taken into account. But there's only so many things that we can do. Not me personally, but yes, it's not a naive question. It's a super important thing as well. Thank you.
Okay, thank you.
Okay,
Hi,
so,
can you hear me?
again.